Hello there. One thing I discussed in the last video is that we can define a conservative force field in the following way. That if you can come up with some scalar field u, such that if you take the gradient of that scalar field u with a minus sign for convention, and you can output the force field, then that force field is conservative, right? Right, and the reason that's such a big deal is because if I determine the work done by my force field along some path c, that's just going to be me taking the path integral of that force field, which now if we have this condition, we can go ahead and just plug this guy in. We're going to have our path integral of grad u dot dr, and now all of a sudden, right, now we can just associate this guy with infinitesimal changes of u, and so this path integral is just going to give us a minus delta u. And so now we can simply associate the amount of work done with the change in this parameter u, this change in our potential energy. Now, as a bit of a warm-up and just to get started, let's make sure that we're totally clear on this step here. Why can I call gradient of u dot dr, why is this equal to what I'm saying is an infinitesimal change in u? Okay, so let's go ahead and do this for Cartesian coordinates. Let's go ahead and remember what the nabla operator here is in Cartesian coordinates. It's going to be like d over dx in the x hat direction plus d over dy in the y hat direction plus d over dz in the z hat direction. And we're applying this to our scalar function u. So we put u in each of those, and now we're dotting it with a dr vector, right? Now this dr vector, which is going to point in some arbitrary direction, right? That means it can have some arbitrary component dx in the x hat direction plus dy in the y hat direction plus dz, right, in the z hat direction, right? And so now if we take this dot product, this is a nice and simple dot product, we're going to have partial u, partial x, dx, plus partial u, partial y, dy, plus partial u, partial z, dz, right? And so now I think you can very clearly see that each of these terms are corresponding to infinitesimal changes in u in each independent direction. So this term here, this is going to correspond to the infinitesimal change of u. If you move in the x direction, this is going to correspond to the infinitesimal change in u if you move a tiny little dy in the y direction, right? And this is going to correspond to the infinitesimal change in u if you move just a little teeny bit in the z direction, right? And so in other words, right, and if you put all of these together, this is going to be the infinitesimal change in u, you know, for moving some arbitrary direction dr, right, which is essentially some combination of translating dx, dy, and dz all at the same time. Okay, so hopefully this makes more sense just to give us a little warm up here and explain why we can associate this guy with infinitesimal changes of u such that when we integrate over our path, it gives us a delta u. It gives us a change in this parameter u, right? We really want that. We want to avoid doing this path integral every time that we calculate work, right? And so being able to determine if your force field is conservative or not is a very big deal. Now you might just say, well, the easiest way to determine if my force field is conservative then is to think, can I just come up with this scalar potential u? And sure, that's one totally valid way, but there's a really nice test that I want to talk about in this video, that before you even go about computing out this scalar potential u, you can just figure out if your field is conservative or not. Let's go ahead and think about how. So the first thing we should think about is what happens if I turn these path integrals into closed loop integrals, okay? And so what I mean by that is that if I put my axes down like this, my particle here, it's going to go ahead and it's going to start out at some position Ri. You know, normally its path would go to some final position R final. But what happens if it has some closed loop? In other words, the particle traces out some trajectory and it reaches the exact same point that it started out as, right? And this is my closed loop C. Well, if that force field is conservative, then what's going to happen to this delta U, right? A delta, you just take the final minus the initial, then I'm going to have minus U at the exact same location, right, as where I started. And so these guys here are just going to cancel out, and I'm going to have 0. Ooh, that's a really big deal, right? That for a conservative force field, the closed loop integral is equal to 0, right? And this would have to be true for any closed loop C. This is going to have to be true for any closed loop C. Alright, so are we super clear on this point? Let me make this even more clear by proposing, one kind of test that we might do to check if our force field is conservative with the knowledge that we know right now. If I have some region of space, I'm going to call this R, and I want to see if my force field is conservative in this region of space R. One thing I might be able to do is just start proposing a bunch of little arbitrary paths in the space. Maybe a path like this, maybe a path like this. Look, they're all closed paths, right? Another closed path like that. Maybe a closed path like this. And what I would have to show for all of the closed paths in R, the path integral goes to 0, right? The path integral for all of these little closed loops would be 0 in the region R. Still, totally inefficient test, right? We would have to propose an infinite number of closed loops, but we get the concept, right? Allow me to go ahead and zoom in on one of these loops, okay? So I'm gonna blow this guy up here. Okay, we can take a look at it a little bit closer. Let's say in this trajectory, my particle is circling this way. Okay, I'm indicating it with this arrow. So we're looping around just like this in the counterclockwise direction. What happens if we subdivide this purple path? Okay, and the way that I'm going to show this is I'm going to put this in blue over the path. Okay, and I'm going to split this path up into two paths kind of like this. You see how now they each have this interior section? So what I'm saying is the particle first travels on this first path, right? We have this closed loop. I'll call that closed loop A. And then the particle next, it traverses this blue path here, right? And I'm going to call this path B. And you know what? I'm going to call this purple path here, I'm going to call this the total path T. Right? If you see where I'm going with this, right? The closed path integral along path A, and I'm not going to write the interior of these integrals for a bit. Let's just get the concept across. Plus, the closed path integral along path B is going to be equal to the closed path integral along path T. Why? Right? Because look at what we've got going on here. We have this, for each of these paths, A and B, we have these exterior bits. So here's the exterior on path A, and here's the exterior on path B, and then we have the interior bits. And notice how the interior bits are going in opposite directions. So those are going to cancel out. So let me write this out super explicitly, okay? So these closed paths, so I'm going to break down this path A into two components. I have the path integral of A on the exterior plus the path integral of A on the interior. I can do the same thing with B, plus the path integral of B on the exterior plus the path integral of B on the interior. These interior bits, because they're path integrals that traverse the same path but in opposite directions, these guys here, they're going to cancel out with each other. And so that's just going to leave me with me tracing out the exterior path of A and the exterior path of B And of course, you put those two things together, and that's going to give you the total path integral t, right? Now, as soon as you see this for 2 paths, right, and I'm not going to go and show this for 3, 4, 5, 6 paths, as soon as you see it for 2, you can imagine in your mind that we can subdivide, you know, basically any closed loop down into a bunch, lots and lots of little, you know, closed paths. And if their exteriors, you know, I'm drawing this roughly, if their exteriors are adding up all together to give you, you know, the net resulting total path, and their interiors all are going in opposite directions, all the interior bits are just going to cancel out with each other, and you're just going to be left with the total path integral, right? Now we're dealing with calculus, right? So we can already start imagining taking the limit as these little circulations here get smaller and smaller and smaller, and we fit an infinite number of them into the purple path t. So this next concept here, this concept of an infinitesimal circulation or an infinitesimal closed path integral, is going to become extremely important. All right, so that's the next topic here. Let's go ahead and look at one of these. What is an infinitesimal closed path integral? Right? Let's start thinking about this concept here. An infinitesimally small closed path integral. So let's go ahead and imagine taking one of these paths here, okay? I'm going to blow up the blue path, okay? I'm going to take this little blue path here and I'm going to blow it up for us. Okay, and we'll go back to calling this path C. Now, for the finite integral, right, then we can just define the path integral as normal, right? Now the thing to emphasize is that this path C is going to enclose some area now, right? There's an area within this path. This shaded region within the path is going to have some area. I'm going to call it delta A, okay? And so I'm just going to take my path integral. I'm going to just divide it through that size, delta A. And now let's just imagine what happens if I take the limit as delta A goes to 0. Do you see what we've got going on here? I'm taking the limit as delta A goes to 0. That means I'm shrinking my path until it has practically no area enclosed within it. And the final modification, okay, the final modification I'm going to make is I'm going to go ahead and we can define directions of areas, and this is particularly useful just when working with 3D space, okay? So it might seem like an arbitrary move right now, but it's still an important one. And what we do is we can define a unit normal to our region, right? If this is a flat sector, you know, and everything is going to locally look flat, you know, if you're looking at infinitesimal bits of area, right, then we can define a unit normal vector, right? It's just normal to the plane of this kind of surface area bit here, right? So I'm just going to go ahead and introduce this little unit normal, and that's going to be called n hat, right? And so I've packaged this idea up for us, okay? This is how we define the notion of taking the infinitesimally small closed path integrals of our force field, right? And so we define this as the curl of our force field F, okay? And if we evaluate the curl at a specific location, we'll say a point P, then the concept here is this is effectively finding the infinitesimally small closed path integral of F centered at the point P. Right? Let me make that E a little bit nicer. There we go. So this notion here of curl is finding infinitesimally small closed path integrals. Taking the curl of your function, you don't necessarily have to evaluate at just one point. It's just like taking a derivative, right? It's going to give you some function, hypothetically, right? And then you could plug a point in to find the curl at a specific location. All right, now let me go ahead and put this all together though. This total loop T here, this finite loop, is going to capture a finite surface S, okay? It's going to enclose some finite surface S. This surface could be flat, it could be curved, right? Depends on the shape of the loop. So what we can do now is we can take all of these little curls, we can take all of these infinitesimally small closed path integrals, add them all up together, and that's going to give me, remember, the little interior bits, they're all going to cancel out with each other, and that's just going to leave me with the closed total path integral T. But what we can imagine, right, is that each of these now, these little infinitesimal loops, we're going to match them up with little infinitesimally small surface area elements. I'm going to call those surfaces ds, okay? Right? And each of these little ds patches, they're each going to have, you know, they're going to have some direction, okay? They're going to have some unit normal vector pointing off of them. Call that n hat. So if I want to evaluate, okay, if I want to evaluate the closed loop integral along my total path T, then I can simply add together, right, which is effectively going to be taking a surface integral along my surface S. I can add together all of the little infinitesimally small closed path integrals on the surface S, right, which you get by taking the curl of your field F dotted with your little ds in the normal direction vectors. You know, and sometimes you call these guys ds, just like this for shorthand, right? Because again, as I'm kind of indicating here, if I take all of my little infinitesimally small closed path integrals and I add them all together along the surface S, all of these little interior bits are going to cancel out, and I'm going to be left with just the perimeter, just the closed loop integral on the outside, right? And that is my path integral of T. Okay, so this guy here, this is called Stoke's theorem. Stoke's theorem, it's super duper important, appears all the time. That's the logic behind it though. All right, so now let's go ahead and let me emphasize this last point here. Okay, remember the whole point before, we had to calculate a bunch of different path integrals of a bunch of different loops, an infinite number of loops within a region R to show that the force field was conservative within that region R. Now we have a very simple condition. As long as we show that the curl of your force field F is 0 everywhere inside of the region R, then what's that going to do? That's going to make this guy equal to 0, and so, you know, your circulation integrals are going to be equal to 0 within that region, also for any proposed loop that you can come up with. And so the moment that you show the curl of your field is 0 everywhere inside a simply connected region R, then F will be conservative in that region. Okay, so all that you got to do is you got to show that the curl of your field F is equal to 0 everywhere in the region that you're interested in, and then you'll know F is conservative, right? And of course, you also have to know, right? Let me also just emphasize this last point. F cannot be a function of time. Your force field also can't change with time, okay? I've been assuming that the force field in this video has just been static, right? So really you have these two conditions here. I'll talk about how to actually compute curl in an example problem in the next video, okay? But it's more or less just taking your nabla operator and crossing it with your field F, which is not difficult at all. If you enjoyed this video, found it helpful, let me know in the comments and consider subscribing to the channel. I love to hear about people getting on board. But other than that, thank you so much for watching.